Okay, so these notes are on radioactive dating, which is 19.5 and 19.6 in your book. Radioactive dating uses the radioactive decay, so we talked about those in our notes last night, of certain elements to tell the age of a rock or a fossil. And so, if you know, for example, let's go back a little further. You know that we as people have carbon in us. We're carbon-based life forms. So, and you also know that most of the carbon in the world, even in the universe, but let's talk about the world right now, is carbon-12. 6 protons and 6 neutrons. But there's also some carbon-13 and there's also some carbon-14, and those exist in the world. And so also in us there are similar amounts of carbon-12 and carbon-13 and carbon-14 as we see in the rest of the world. And so we actually have radioactive carbon in us. And it's not a big deal. It doesn't harm us or anything like that. But as we grow, we get more carbon, and so we are going to get more carbon-14, but in the same ratio as we have now. Similarly, as we lose weight, we're going to lose carbon, and we'll lose some carbon-14, mostly carbon-12, in the same ratio. But when we die, the carbon-12 in us starts to decay, give off particles to become more stable. And therefore, if we know how long it takes to decay, and we know how much something started with, we can figure out how old that thing is. So when you hear scientists say, this dinosaur fossil is 70 million years old, what they're doing is they're tracking the radioactive carbon in that bone since the dinosaur died. Now, obviously that doesn't include how long it lived, but on the number of millions of years, it doesn't matter if it lived 60 years or 20 years or 100 years. That's all the same when we're talking millions of years. If you're talking about rocks, then normally you're tracking something like uranium in the rock, and you're tracking it from when that rock was an igneous rock. So if you go back to the rock cycle, you may remember that igneous rocks are the rocks that are spewed forth from volcanoes, and then they harden, and they can go through lots of things. They can be worn away, and then the sediment can be changed into sedimentary rock, or they can be exposed to heat and pressure and can be changed into a metamorphic rock. But the radioactive elements in that rock start to decay after it hardens as an igneous rock. So again, when you hear this rock is so many millions or so many billions of years old, that's since it was hardened into an igneous rock. Now, if that igneous rock at some point in time ends up back in the mantle and melts down, and then is spewed forth from another volcano somewhere and hardens again as an igneous rock, almost like the time we're measuring from starts over. In order to understand this, you have to understand something called a half-life. And a half-life is the amount of time it takes for half of an amount of an element to decay. Now, there are some pretty complex mathematical formulas for this. We're not going to worry too much about those. We're going to look at this more from a conceptual point of view. We are going to use some math, but we're going to stick to mostly conceptual. So, for example, radium-226 has a half-life of 1,620 years. So if you start with 1,000 atoms of radium-226, in 1,620 years you will only have 500 left, 500 atoms. Now realistically, we usually talk about weight. If you have 100 grams of radium-226, or we talk about these things called moles, if you have 100 moles of radium-226. We're not going to worry too much about that. The point is, in 1,620 years, you will have half of what you started with. So half of 1,000 is 500. Now what's interesting is, in another 1,620 years, you don't end up with zero. It's not like, so you decreased by 500, then you decrease by 500 more. In another 1,620 years, you end up with half of the 500 left. so that would be 250. And then you end up with half in another 1,620 years, you end up with half of the 250, which would be 125. So you keep cutting it in half every 1,620 years. The shorter the half-life, the greater the radioactivity. So for example, radium-226 has a half-life of 1,620 years, uranium-238, and by the way, for those of you who are going, what's 226, what's 238? Those, remember, that's the isotope. It's the mass number. So we say uranium-238, that's the uranium that has 238 protons and plus neutrons in its nucleus. I don't have a periodic table in front of me. I think uranium is maybe element 92. It's somewhere in there. So then it would have 92 protons and then 238 minus 92 neutrons. But at any rate, uranium-238 has a half-life of 4.5 billion years, meaning radium-226 is more radioactive. Half of it is going to decay faster than half of an equivalent amount of uranium-238. So you can think about how we would use this to date things, and by date I mean tell the age of something. Let's think about money. If you know that somebody spends half their money every day, and you know that they started with $100 and they have $25 left, you should be able to figure out how many days it's been since they started spending their money. So see if you can actually figure that out. If they have $25 left, they started with $100, and they spend half their money every day, they have a half-life of 1 day spending, how many days have they been spending? So if you figure this out, you should say, well, after 1 day they would go 100 to 50. After 2 days they would go 50 to 25. So they've been spending for 2 days. So again, if you have questions, please feel free to include them on the notes.